Did you know that during the lifetime of every oil well, there's a continuous aging process going on? As oil and gas are removed from the reservoir, water gradually seeps into the formation. So, generally speaking, older wells produce a greater amount of water. And that's why water storage tanks, like this one, are necessary. Because we aren't just pumping oil out of these wells, but a mixture of well fluids made up of oil, gas, and water. Now, this mixture is so thoroughly blended that it can be pretty difficult to break into its three basic parts. Often this mixture, or emulsion as it's frequently called, must be specially treated before it will separate into its components. Much of this process is carried out in a heater treater. This is the first section in the module, Emulsions and Vertical Heater Treater Principles. Section 1 introduces you to the basics of emulsions. To begin, we'll take a look at how they're formed and why they must be treated. Then we'll examine several different ways that emulsions can be treated. This whole problem of emulsions is dealt with in many ways. Frequently, production separators or free water knockouts will be used in conjunction with heater treaters. It's an expensive process, so to ensure that treating is done at the lowest cost, all of the equipment must be properly sized, carefully installed and maintained, and then continuously monitored. Complete, accurate records of water flow, chemical usage, fuel gas, to name a few, should be kept for each lease. But let's concentrate more closely on emulsions. Now, some of the water in the wellhead fluid separates easily from the oil, thus it's called free water. But the rest of the water is mixed so completely, or emulsified, that treating is necessary to remove it from the oil. In an emulsion, one of the liquids is spread out, or dispersed, throughout the other in the form of small droplets. In oil field emulsions, water is usually dispersed in oil, often called a water-in-oil emulsion. Now, the opposite, oil-in-water emulsion, can also occur. Depending upon the type and amount of emulsifying agent present, an emulsion may be easy to break, or loose, or it may be hard to break, or tight. An emulsifying agent promotes the formation and stability of an emulsion. The agent collects on the surface of water droplets, forming a tough film which prevents the droplets from joining together to create larger droplets. Asphalt, resins, paraffins, and oil-soluble organic acids are emulsifying agents commonly found in oil field emulsions. Each oil field will have its own individual compound of emulsifying agents. In order to break an emulsion, the film must be neutralized or destroyed through treatment. The treating is usually done in the field using various types of equipment and by adding chemicals to the emulsion immediately after it's produced. As I mentioned before, the stability of an emulsion, or the degree of difficulty to break an emulsion, depends upon several factors. Emulsification depends on the type of agent and the conditions under which the emulsion is produced. Oil with a high resistance to flow or viscosity tends to keep water droplets in suspension, creating a more stable emulsion. Oil which has a low API gravity tends to keep water droplets in suspension, also creating a more stable emulsion. In most cases, the smaller the percentage of water contained in the emulsion, the greater the stability of the emulsion. Increased agitation causes greater dispersion of the water droplets, thus increasing emulsion stability. Small water droplets give more stability to the emulsion since they're lighter and don't settle out as readily. Old emulsions die hard. The longer an emulsion remains untreated, the more difficult it is to break. The water produced from reservoirs may vary from a small fraction of 1% to as much as 99%. Now, that can be a lot of water. Pipeline companies are not about to pay for any of the water which remains in the oil, so they very carefully monitor the water percentage. Most of this water must be removed before the oil is delivered to the pipeline. In many cases, this requires treating the emulsion. Now, no two emulsions are alike, and even the emulsion from a single well changes throughout its lifetime. And these changes require careful monitoring so that the treatment process can be adjusted as necessary in order to maintain maximum efficiency. It's important because revenues are affected by the gravity of oil. Natural gas also generates considerable revenue, so it must also be monitored closely to maximize yield. treating emulsions may require one or more procedures, like allowing settling time, applying heat, injecting chemicals, using electricity, or operating mechanical devices. Let's look at each of these in a little more detail. The time needed to completely separate an emulsion is called settling time. Now, the settling rate of a water and oil emulsion is affected by viscosity, size of water droplets, and gravity. Now, let me show you what I mean. I'm going to make my own emulsion using water and oil. Pour in the oil. Add a little water. Tightly screw on the lid and shake. Now, this is roughly the kind of emulsion which flows from the wellhead. If the oil has a high viscosity, that is, it's very thick, then the water droplets cannot move without considerable resistance and will not settle out easily. The settling rate is also affected by the size of water droplets. Smaller droplets are lighter and take longer to separate through settling. If the difference in API gravity between water and oil is small, then separation is slow. However, water weighs more than oil and will eventually settle to the bottom of a vessel. Now, some emulsions can be adequately treated through settling alone. Tighter emulsions need additional treatment procedures designed to speed up settling. The ideal way to treat oil is without heat, but treatment frequently requires heat to speed up separation. Let me show you what I mean. I'm going to take another jar and make an emulsion exactly like the first one. Pour in some oil. Add water. Tighten the lid. And shake. But with this jar, I'm going to loosen the lid and very carefully apply a little heat, just for demonstration. Heat alone will not break an emulsion, but it aids in several ways. Heat causes the water droplets to move around faster, striking each other with greater frequency and force. As the droplets collide, the film of emulsifying agent ruptures and larger, heavier droplets form. Now, these larger droplets yield to the gravity differential and gradually settle out. Heat lowers the viscosity of oil, allowing the water droplets to settle out more easily and quickly. And heat speeds up chemical action. Chemicals make the film surrounding the water droplets rigid. As heat is applied, the water droplets expand, breaking this film. The water droplets can then merge into larger ones and settle out. As you can see, there is a difference. In just a few seconds, the heated emulsion has separated more than the unheated emulsion. But heat must be applied only as necessary. Too much heat will waste energy and cause greater wear on the equipment. Also, excessive heat can burn off the valuable lighter ends of crude oil, changing the oil's gravity and resulting in lost revenue. Emulsion-breaking chemicals are injected into the well stream ahead of the heater treater. Now, these chemicals react with the film around water droplets, destroying or neutralizing the film. Now, this allows the droplets to combine or coalesce and separate from the oil. Now, there must be sufficient agitation to allow the chemical to contact each water droplet. The amount and type of chemical used affects how easily the emulsion breaks and how much time is needed for settling. Also, the warmer the emulsion, the less chemical is needed. Too much heat or chemical will cause the undesirable breakdown we discussed earlier. And when used in conjunction with heat and chemicals, electricity will separate oil and water. The vessel used in this process is called a chem-electric heater. Its design and operation will be examined in another module. Devices such as gun barrels and free water knockouts are used to treat emulsions. A gun barrel is a settling tank which separates oil and water in the field. After emulsified oil has been heated and treated with chemicals, it's pumped to the gun barrel for gravity separation. Gun barrels are still common, especially in older fields, but they're frequently replaced by heater treaters. A free water knockout removes excessive water from the produced fluid ahead of the treating unit. On some knockouts, a filter or excelsior called hay catches particles of oil entrained in the free water as it passes through the filter. Through gravity, the free water is drained off, leaving only emulsion to pass on into the treating unit. The free water knockouts prevent overloading of the treating vessel and also save fuel. In this first section, we've looked at the basics of emulsions, how they're formed and why they must be treated. We examined in detail some of the factors that affect settling time, and I demonstrated how heat speeds up separation. Now in the next section, we'll look at the components that make these devices work. But first, take some time now to stop the videotape, think about everything we've covered so far. Then fill in the blanks and answer the questions in your student manual. While you're away, I'm going to go clean up a couple of jars over there and get ready for our next section, heater treater design. See you in a few minutes. You know, dealing with emulsions can be a dirty business, but it has to be done. And that's the job of the heater treater. The vertical heater treater combines all the equipment necessary to treat an emulsion. This is the second section in the module, Emulsions and Vertical Heater Treater Principles. Section 2 will cover the basic parts of heater treaters and, briefly, their role in the treating process. The vertical heater treater is the most commonly used emulsion treater in the oil industry. Used for three-phase separation, it may include one or all of these components or sections: oil and gas separator, a free water knockout, heater, water wash, filter section, stabilizing section, and heat exchanger. Heater treaters are designed for the well fluids of each particular lease. Any number of modifications to the basic design can be made. For example, both the size of internal sections and the amount of heat required may vary. Sometimes a filter or hay section is needed. Selection of the right treater design depends on many factors such as climate, amount of well fluids to be handled, and the characteristics of the emulsion being treated. In any case, we want the treating to be done at low cost, with the least addition of heat and the smallest decrease in oil gravity. The chemically treated emulsion enters the heater treater at the top, flows down to the bottom, and then back up through various treating sections. Each step brings the emulsion closer to complete separation of oil, gas, and water. Let's identify the external components of the heater treater. Emulsions enter the heater treater through the inlet line, which is located inside the heat exchanger. The heat exchanger heats the incoming emulsion and cools the outgoing treated oil. The safety device may be a relief valve, rupture disc, or even both. They're designed to open if too much pressure builds up inside the treater. Gas exits the heater treater through the gas outlet and then into the gas line. Located on the gas outlet line, the gas back pressure valve maintains sufficient pressure to dump the liquids. All sections of the treater operate at the same pressure. To maintain proper operating pressure, some heater treaters have a make-up gas line with a regulator. The gas supply line provides gas pressure to the water and oil dump valves. Now, this line usually runs from the top of the treater down to a drip trap. Oil leaves the treater through the oil outlet located near the top of the settling section. The oil dump valve is located on the oil drain line. This valve opens and closes depending on the weight of the fluid it's handling. More oil in the line opens the valve, and less oil will close it. The oil dump valve operates by gas extracted from the emulsion or through mechanical means. The water outlet line removes free water from the heater treater. A water siphon maintains a predetermined oil and water interface level. Now, this system is usually attached to the outside of the unit, but in colder climates, an internal siphon system is specified. You may also hear this called a water leg or water siphon box. The adjustable siphon nipple, located on the water siphon line, can be raised or lowered to change the water level within the heater treater. The water dump valve operates either by gas provided from a gas supply line or mechanically by a lever attached to a diaphragm. This diaphragm opens or closes the valve depending on the amount of water in the line. More water opens it and less water closes it. The firebox houses the gas burners which provide the heat source for the heater treater. This metal cylinder, called a stack, vents the exhaust gases after they pass through the fire tubes. Sight glasses allow the pumper to monitor the oil-water interface within the treater. This helps maintain proper levels and efficient operation. Located on the bottom of the heater treater, the drain allows emptying of the vessel for repairs or removal of accumulated solids. The thermometer indicates the temperature at which the emulsion is being treated. The thermal well provides a location for the temperature probe. A thermostat connected to the probe maintains the preset treating temperature inside the vessel. Now that we've identified the major external components, let's look at the internal sections. As we look at the treater from top to bottom, the locations of the internal sections are the gas separation section, the settling section, the heating section, and the free water knockout section. Emulsion enters into the top section of the vertical heater treater. The initial separation of gas and liquids begins here. The mist extractor removes any tiny particles entrained in the gas stream before leaving the vessel. Condensed fluids travel from the gas separation section to the free water knockout section through a vertical tube called an emulsion downcomer. In the settling section, located between the gas separation section and the heating section, final separation of oil and water takes place. Metal traps or baffles obstruct or collect fluids, causing the water droplets to merge. Now, this action increases the travel of fluids through the treater. The weir box provides a level-controlled, open-top chamber for collection of oil. After the oil reaches a preset level, it leaves the settling section, flowing into the heat exchanger tube. Gas is vented through the pressure equalizer to maintain consistent, even pressure inside the vessel. Located between the settling section and the free water knockout section, the heating section applies heat to the emulsion. A firebox containing the gas-fired burners heats the fire tubes, which in turn heat the emulsion. Now, this section of the heater treater is the area most susceptible to failure, so the lowest possible temperature should be used to prevent undue wear on the fire tubes. Sometimes, in colder climates, a special steel housing bolted around the treater is added to maintain high temperatures. Also, insulation is used more and more often in all climates to retain heat and save fuel. Located in the very bottom of the heater treater, the free water knockout section allows the water to settle out and finally leave the vessel through the water dump valve. In water washing, large water droplets coalesce with small water droplets and settle out. Excelsior may be used to break a tight emulsion. It's usually packed in the top part of the water wash section, installed through a manhole. Excelsior acts as a coalescent pack to aid in separating oil and water. Its amount varies depending on the emulsion. In order to operate properly and safely, every heater treater is equipped with safety devices and monitoring features. A flame arrestor fits on the front of the firebox. A series of aluminum vanes placed closely together disperses heat generated in the firebox into the air. This reduces the possibility of fire spreading outside the vessel. The safety relief valve, or pop valve, is designed to open at a preset pressure level to relieve excessive pressure within the vessel. The rupture disc consists of a thin piece of metal installed in a flange. The metal is designed to burst at a predetermined pressure level. This pressure is usually set at or below the maximum safe working pressure of the treater. The fuel gas scrubber prevents entrained liquids from passing into the burner along with the fuel gas. Should the scrubber become filled with liquid, a float rises and shuts off a valve. This stops the flow of gas to the burner, preventing the possibility of an uncontrolled fire. A drain valve is fitted to the scrubber to remove collected liquids. The pumper should check and drain the scrubber every day. Sight glasses are the best way for the pumper to see if the treater is doing its job. Should the sight glass break and stick wide open, a safety feature within the gauge will cause a steel ball to seat, shutting off the flow. In this section, we discussed the external components and internal sections of heater treaters. We also looked at the various safety devices built into the treater. It's important to remember that heat and pressure must be handled with great respect when working on or around treaters. Well, it's time again to stop the videotape, fill in the blanks, and answer the questions on your student manual. I'll see you again when you're finished. That should take care of the fuel gas scrubber for today. Let's get started on our next section, heater treater operation. This is the final section in the module, Emulsions and Vertical Heater Treater Principles. In this section, we'll cover the flow of an emulsion through a vertical heater treater. We'll also look at a vertical heater treater operation and some symptoms of improper functioning. Since chemicals are usually injected into the emulsion upstream from the heater treater, the treating process has already begun by the time the emulsion reaches the treater. Remember, the emulsion enters the top of the unit into the gas separation section. It falls through the emulsion downcomer into the free water knockout section. Then the emulsion travels upward through the heating and settling sections. Let's take a closer look at each section. As the emulsion flows through the heat exchanger, it's preheated by the heat of the outgoing oil. Now, this reduces the amount of heating necessary in the heating section. Also, the settling time for incoming oil is decreased, and the outgoing oil is cooled to a more desirable storage temperature, minimizing vaporization and maintaining higher oil gravity. Preheated emulsion enters the vessel, splashes over a pan, and flows into the downcomer. Now, on its way down, the emulsion releases free gas due to the agitation created as it strikes the diverter plate. The gas leaves the treater through a mist extractor at the top of the vessel. As previously discussed, the mist extractor removes tiny liquid particles still entrained in the gas. After leaving the gas separation section through the downcomer, the emulsion enters the free water knockout section. Now, here, most free water quickly settles out, and the remaining lighter liquids move upward through the water, which acts as a heated wash. As the treating process continues, the siphon system removes excess free water. The water section of vertical heater treaters occupies about 60% of the fluid column, leaving 40% for the oil and gas section. There are several things happening in the heating section. Here, the emulsion is heated as it passes around the fire tubes. Next, fluids rise upward through the heat retainer baffles, where water collects on the baffles and falls to the bottom free water knockout section. Released gases and vapor rise into the gas separation section. The heated emulsion in the settling section also releases gas. This gas is vented back into the inlet chamber in order to maintain equalized pressure in every section of the vessel. Heat, chemicals, and gravity work together in the settling section, quickly breaking the emulsion. Finally, the clean oil flows out of the treater through a weir box. A weir is a dam-like structure which maintains liquids at a specified level. The oil flows down the outer shell of the heat exchanger, through the oil dump valve, and into a stock tank. The siphon system maintains the water level in the vessel. Water in the free water knockout section rises into the water siphon and flows over the adjustable siphon nipple. It then leaves the unit through the water dump valve. Since water seeks its own level, with just water in the treater, the water level on the water siphon will be equal to the water level inside the treater. So by changing the position of the siphon leg, or nipple, the water level can be changed to maintain the oil-water interface. Certain treating problems may require this interface level to be raised or lowered, but this adjustment isn't frequently needed. The added weight of the oil on top of the water